Okay, everybody, let's start then. It's my great pleasure, and we're very excited to have the keynote by Prith Banerjee today, this morning. So Prith is currently the Chief Technology Officer at Ansys, a company that works on simulation technologies, and he will be talking today about digital twins, challenges and opportunities in various industries. So Prith has had an illustrious career over the years. He actually started out in academia, initially as a professor at the University of Illinois in Chicago, and then later also as Dean of Engineering at the same university. And he was also the department chair of EC in between at Northwestern University. At some point, he went into industry first by launching several very successful startups. Excel chip, which was later acquired by Xilinx, prominently among those. And that made him transition into the industry roles more and more. Before joining Ansys, he held various roles as first vice president of research and director at Hewlett-Packard Labs, and later in various vice president roles at companies such as Schneider Electric, Accenture, ABB, for example. He's also currently on several boards of companies, so very active in the industry, both in research and previously in academia. His research interests broadly are in electronic design automation, parallel computing. He has co-authored over 350 research papers and supervised more than 37 PhD students. So like I said, phenomenal career so far. He's also a fellow of ACM and IEEE, the recipient of the 1996 ASE Terman Award and 1987 NSF Presidential Award, which is now called the Career Award. So again, we're very fortunate to have him give the keynote today, talking about digital twins, which is an exciting topic for the simulation industry. So Prith, the floor is yours.
Thank you very much, Andreas. Thank you for inviting me. And it's an absolute pleasure and honor to speak at this conference. I have attended, obviously, the conference has evolved over the years, but I used to be a very active participant in the EDA industry, and great to hear my former friend, Raul, give the wonderful obituary. I know all these people in the industry. So what I'm going to talk about.
One quick note, I need to quickly mention to the audience that we are recording this keynote, including the Q&A session at the end. And if you want to pose questions, please use the Q&A window in Zoom. So just as a note. All right, sorry, Prith.
No problem. So as Andreas said in my introduction, I was fortunate to have worked on the topic of digital twins for the last literally 10 years. I started working digital twins when I was at HP Labs, had some very early work on a project called the SENSE project, Central Nervous System for the Earth, getting sort of collecting data from different sensors and then building analytics models to predict the future state. Then when I was a CTO and EVP at ABB, I was involved with building their Ability IoT platform to connect all their assets, their robots and transformers and so on, and to try to do predictive analytics of those assets. Then when I was CTO at Schneider Electric, I did the same thing with their breakers and panels, helped them build the EcoStruxure IoT platform. But when I was in those positions, I rapidly found out that the traditional approach of using pure data analytics-based digital twins, while very relatively easy to do, has its limitations in terms of accuracy, which I will talk about. And so I was always interested in, is there a way to take physics-based simulation to complement, add to the area of digital twins and make it a lot more accurate? And that's how I got attracted about Ansys. I started using Ansys tools when I was at ABB and Schneider, and then ultimately I joined the company as CTO. So I'm going to talk about this very, very interesting topic that I've been literally working on for the last 10 years, and essentially the challenges and opportunities. So will essentially talk about what is digital twin. Again, some of you in the audience may know a lot about it, but others may not, so I'll just give a quick overview. And then I will introduce a role of physics simulation in digital twins, essentially the challenge that I faced when I was at ABB and Schneider. And then most recently, what we are doing is we are combining physics and data analytics together in what is called hybrid physics AI to build a complete analytic solution. And this is really the latest sort of technology trend in this industry, and there are other companies who are trying to do this. But I will highlight to you what we are doing in this area. And then if I have time, I'll talk about some of the ecosystems in digital twins that the conference attendees may be interested in participating, like Digital Twin Consortium and so on. That's sort of mine, but the main things are the first 2-3 topics that I will cover. So the first topic is essentially providing an overview of digital twins and some example case studies, right? So the term digital twin was actually coined by Michael Greaves in 2002, more than almost 30 years ago, within the context of sort of NASA and aerospace and so on, where the idea was you have a physical asset. There's sort of 3 characteristics of a digital twin. You have to have a physical asset, then you have to have a model of that asset, which is the virtual asset. And people oftentimes confuse a digital twin with just a simulation model. What makes a digital twin is a third thing, which is two-way information flow from the physical asset to the digital asset, and from the digital back to the physical. This is what makes a digital twin. So essentially you have a physical asset and a digital asset. That model can be based on analytics, or it could be based on physics. And that's sort of the core part of my conversation. And then the two-way information flow between the two parts, right? How many sensors do you put in your system, right? The more sensors you put, the more accurate the digital twin becomes. So the question is, suppose I have an asset where I can put 1 million sensors. Yes, it can be very, very accurate, but can you do it with only 10 sensors? Can you do it with 100 sensors? And where is the accuracy trade-off, right? So it's a phenomenally interesting technical area. What we have found is, and the reason people are excited about digital twins, the whole industry is interested, is because it has these 3 advantages. One is it can enable customers, right, to increase revenue, to build whole new products like sort of compressed air as a service, which I'll talk about. It can allow you to reduce costs and essentially therefore help both from the top line and a bottom line, right? And we have seen examples of cost reductions as much as $800 million per year. We have seen more than sort of 50% of industrial companies using digital twins as we kind of talk to them. So it's a very exciting industry. Now, and that's kind of what I mentioned, that the advantage of digital twins is growing top line revenue. So what happens, an example of that is, suppose you are a compressor company, right? And you sell compressors for $100,000 or whatever. Now, instead of selling compressors, you start selling compressed air as a service. So essentially you give the compressor to the customer, and you are responsible for maintaining the compressor, right, for like 10 years. And so you are motivated to do improve predictive analytics, doing all the preventive maintenance and so on. So the compressor is up all the time. And essentially you're monetizing it through compressed as a service. That's an example of top line revenue. Example of bottom line costs is where through these, if you have an asset, through predictive analytics, you actually manage your costs because it is easier to diagnose where the problem is, and you don't spend all your time in trying to find out, troubleshoot where your problems are. So essentially, and the third thing is to gain a competitive edge. Many of our customers that I talk to them, right, are using digital twins to complement the physical assets that they're selling. So let me go into the sort of different areas that people have used digital twins. I mentioned that digital twins were started in the aerospace industry, right, with the phenomenal work done at NASA and so on, right? But the idea is that you have a aircraft engine, and most people, know of this use case, right? And typically these engines, right, you have to do maintenance every, say, 20,000 flight hours. So you fly the plane 20,000 hours, and then you take it to a hangar, and you replace all the blades and so on and so forth. That 20,000 hours is based on an average case of all planes, all engines that are flying, etc., right? But a particular plane, right? This United Emirates flight going from Dubai to say Calcutta, right? It is probably seeing a lot of pollution and so on, and that particular engine needs to be cleaned up faster, right? Instead of 20,000 hours, maybe in 10,000 hours. So if you could have a digital twin of that particular engine, right, then you can sort of predict how much those blades will get impacted, whether the engine oil get messed up or not, right? And so that requires you to collect environmental data about the air pollution from the flight from Dubai to Bangalore and so on and so forth. And that is what people have started using in the airline industry. And so, so the airlines, right, can essentially keep the uptime of all the aircraft running much, much higher, right? Because of preventive maintenance and predictive analytics. The same thing has been done in the automotive industry, right? We all know about the connected car, Teslas and so on. And they have phenomenal capabilities now of taking that physical asset, which is the car, and the model of the asset, which is shown on the left-hand side, right? And just constantly monitoring what the car is doing, and therefore driving much more improved efficiency of driving the car, right? By having a digital twin. In the area of manufacturing, people talk about these different large machines like injection molding machines or lathes or whatever, etc. You have a bunch of assets, right? So if you can maintain the uptime of all the assets, it can help in driving up what is called the operating equipment efficiency, OEE metric, if you have a really good idea of those different assets, right? And how those assets are degrading with time, right? And that translates to direct revenue, the manufacturing output from your industry. People have done digital twins in buildings and infrastructure as well as in oil and gas. In oil and gas, large wells, right? You have very, very complicated equipment, lots of valves and pumps and so on, and all these things can fail, right? Including the worst case scenario of Deepwater Horizon that had an explosion, right? If, for example, the oil and gas company, right, had a way to monitor this thing, they could have prevented the oil and the Deepwater Horizon accident. So there are tremendous applications of digital twins in all kinds of industry, which is why the whole market, right, is expanding, right? So essentially, if you look at the digital twin market today, right, it's less than sort of $5 billion, but it's supposed to grow to $26 billion by 2025. Tremendous growth. Why? Because people are using digital twins in different industries, in the operations phase of assets, in the design phase of assets, and the analysis phase of assets. And I just don't have time to go into those different things as an example, but I will highlight how this technology of digital twins has been used in all these different areas, right, through sort of customer examples. I mentioned that digital twins has been used in all industries. I gave you 5 examples of industries, but if you look at the market grew up in the different industries, right? In 2018, about 22% of the digital twins have been in the manufacturing industry, right? And in manufacturing, we are talking of discrete manufacturing, right? When you have a widget and you're building all these widgets, or in and that's sort of like 22%. But it's also used in automotive industries, right? The GM, Ford Motor Company making cars and so on, right? Or in energy and utilities, right? It's about 10%. So that's what is being used today, but it is supposed to grow to, say, the automotive industry will go to about 25% plus, right? By the year 2025. So tremendous opportunity, tremendous growth. So now the question is, why, I mean, what are the different types of how do people build digital twins, right? So I'll do a very, very quick tutorial for the technical audience. I know you know this, but I will motivate why you need physics-based digital twins. So in a normal approach of doing what is called data-driven modeling of digital twins, you take an asset like a transformer from ABB or a robot from Siemens or whatever, right? And essentially you attach sensors to the asset, right? And you connect those assets to an IoT platform like the Ability platform for ABB or the Predictive platform from GE, and you collect data under normal conditions, right? And then essentially you build an analytics model of that asset using deep neural networks. And so the picture on the right-hand side is showing a neural network with 3 hidden layers, right? Again, there's a fundamental sort of theorem called the universal theorem by George Sabenga, which says for continuous functions, if you have a function with inputs x and you have a function y, it doesn't matter what the function is, it can be widely varying and so on, right? With just a single hidden layer, you can approximate, you can literally recreate, right? By creating these weights of these neural networks, right? You can recreate in the output any continuous function. And now if you have multiple physics that are going on, all you have to do is multiple neural networks. And typically people do like 6-stage neural networks. And the beauty of this is through a forward approximation, right? You guess what the weights should be, and then you look at the errors at the output, right? You actually measure the output and you predict it to be this, and you say, okay, then you do a backward propagation and you correct the weights, then you another forward, another backward. So in like 3-4 times, you train this neural network, and now these weights are perfect. They know exactly how the assets perform. This is how deep neural networks work. And the advantage of this is you don't need to know the physics of the assets. It's a totally general approach and it works, right? The disadvantage, it requires lots of training data. We are talking of billions of data sets to train this neural network. Once you train it, it does very well. But the trouble is they only are trained on the models that you have seen, right? So if you have a washer and dryer at home, right? And just before it fails, it will start giving a lot of noise and say, hey, this is an abnormal behavior, therefore it's about to fail, let me fix it. But suppose your washer dryer, before it fails, does not give a loud noise and it just squeaks and what's so. You have not seen it, your neural network will never be able to catch it. So this is the limitation of data analytics-based digital twin. One is, takes a lot of training data. Second is, it is only trained to the failure models that we have seen. You cannot learn unseen failures. This is what physics-based digital twins does, right? So let me give you an example of physics-based. Suppose you could physically simulate how an asset fails with mechanical fluids electronics model, right? Imagine I live in San Francisco, right? I drive by the Golden Gate Bridge all the time, right? So suppose you're trying to model a Golden Gate Bridge failure, right? And you look at all kinds of sort of statistics of bridge failures around the world, and you say an average bridge lives about, say, 50 years, and my bridge is 49 years old, therefore I'll predict it will fail next year, right? That's a very, very approximate way of predicting it, right? The other way is you can say, hey, you observe a crack in the bridge tower, and that you observe it through an IoT platform, it's 12 inches long today. Then what you can do is you can model the stress strain of the bridge with 1,000 cars driving and 1,500 pedestrians running on Golden Gate Bridge, and you can predict that that crack, which was 12 inches today, will grow to 18 inches by next week. You can do that through simulation. Then what you do, and that's sort of the model of the digital twin that I was talking about, right? Then is the two-way information flow. You say, hey, actually measure the crack next week. And if the crack is precisely 18 inches, means your simulation is correct. If the crack is only 60 inches, it means, oh my God, my simulation model is going faster. So you slow down the crack propagation. And if the actual crack is 20 inches, you update the simulation model, speed up the crack propagation. The point of this is if you combine this physics-based simulation with connection, right, with the IoT data, you can make this prediction so much better. And if you say this bridge is going to crack next Tuesday, it will crack. I mean, essentially. So that's the power of physics-based digital twins, okay? So now, given that I have sort of explained the motivation, right? How are we using digital twins at Ansys, right? And so this is before the combination with the hybrid digital twin, which I'll come to later, right? So the sort of current approach to digital twins using physics is this, right? We have a simulation-based digital twin combined with IoT data analytics, right? And using this, we create these things. The advantages are you can create a virtual sensor. What's a virtual sensor? So imagine you have a pump, right? And the pump can have, in the worst case behavior, a thing what's called cavitation. When the cavitation happens, the pump behaves in a different way. But whether the pump is cavitating or not, you can actually find out through putting a sensor inside the pump. Well, as it turns out, if you put a sensor inside the pump, it is a invasive sensor and the pump will stop acting as a pump. So you cannot actually put a sensor inside the pump, right? So then what do you do? Well, through the physics, the fluid physics that is happening inside the pump, right? You can say, hey, here is a little turbulence that I want to create, and because of it, it will create some voltage and a force, and because of it, the pump will work, right? You could create the entire thing with physics, right? Physics-based simulation. So you can create virtual sensors to simulate. You can do what-if scenarios before applying a solution. So for example, you are doing an autonomous car driving, right? And there's these Google Waymo cars are driving around the streets of San Francisco, right? At 9 a.m. in the morning when it is sunny and there's maybe 10 cars and 15 pedestrians on the road, right? Now that use case they are literally looking at. But suppose you want to say, what if there were 1,000 cars on the road and 1,500 pedestrians and a cat and a dog, right? You don't have that actual scenario in the real world, right? But you could do this in a what-if simulation-based approach, right? So there are different things you can do that you normally could not do in the physical, or you may have to wait like 100,000 million hours to run, right? And then essentially using the physics-based accuracy, that example of the bridge that I showed you, it improves the accuracy. And essentially you can create sort of baseline data, failure data using physics. So because of it, a lot of customers have started using physics-based digital twins, right? So what we do is, again, this is our offer, but again, other simulation vendors like Dassault, Siemens, etc., they have similar kind of tools, and I want you to be aware of it. So what we do at Ansys is we have these three phases, right? Where we take an asset, and because we have a lot of simulation capabilities like Fluent for fluid simulation, Ansys mechanical for mechanical structural simulation, HFSS for electromagnetic simulation. So we'll take this asset and we'll model the actual physics, right? Based on the multi-physics interactions. And from those physics, we'll build what is called an approximate model, a reduced order model, ROM, which is pretty much like acting as the original thing, but it's running faster. Think about SPICE, right? I mean, in this area, people talk about SPICE. You can do detailed circuit simulations in SPICE, but SPICE takes forever. So you approximate the circuit simulation in the digital world with ones and zeros, and you extract like a ROM for a digital chip in ones and zeros. That's sort of what is happening with ROMs, right? And so you build a ROM for that asset. And then you have to say, hey, how good is my ROM, right? Is it accurate? So you validate it, and then you essentially deploy it at the field. And this is like a software model in ones and zeros. It is running on an edge device, right? Or on a cloud using Docker containers or whatever, right? In a really much faster. So the original simulation model, suppose you wanted to model a bridge, right? It would take you 1 million hours to simulate the crack propagation. Clearly that is not practical, right? And so you build a reduced order model of that crack propagation of the bridge, and then that thing runs much faster, and you can actually run on an edge device. You put a little ARM chip on near a bridge, and you will add that, right? Take that IoT data, do this, and do a real quick analytics right there on the edge itself. So you can do various deployment scenarios of this Ansys Twin Builder. That is where the state of the art is. So now, just double clicking on how we build these ROMs, right? In case you're interested, right? So depending on the physics can be fluid physics, can be sort of airflow inside a fan or a vent or whatever, or it can be electromagnetic interferences. Whatever the physics is, we can model the physics and build these reduced order models, and these ROM models run in a fraction of a time, right? There are different types of ROMs that we have built over the years, right? One type of ROM is what is called a linear ROM, right? So for systems that are linear, state spaces and so on, you can model it, but only for linear systems, right? Unfortunately, the trouble that most of the things around us are nonlinear systems, like when you have turbulent airflow over a wing shape in a plane, that is not a linear system, right? And so therefore you cannot do the linear ROM. Then you have to use a nonlinear ROM. And within nonlinear, you have this what is called static ROMs and dynamic ROMs. Static ROMs are independent of the time, and dynamic ROMs are dependent on time, right? So you have a time varying kind of a thing that you do. So we have done over the years, we have done linear, nonlinear, static, dynamic ROMs, and we have built these ROMs starting from the core physics. The core physics is like Maxwell, which is our low frequency electromagnetic solver, or the Fluent, which is a finite volume based computational fluid dynamic solver, or ISPAC, which is a thing for our sort of fluid flow, etc., right? Thermal modeling and so on, right? HFSS is a high frequency electromagnetic solver, right? So all of these things, we take those tools and we build those reduced order models. So that's step one, right? That's the build. Then what we do is we sort of validate it and deploy it on an IoT platform. And so we have partnerships with PTC on the ThingWorx platform, Microsoft on the Azure IOL platform. So in fact, right now, today, Sam George, Corporate Vice President at Microsoft, is giving a talk at the Microsoft conference talking about how Azure ML is partnering with Ansys, right, to build digital twins for our customers. So it's a very strong partnership that we have. So essentially, we take this asset, build a simulation model, and you deploy it on an IoT platform, right, in the different verticals of automotive or aerospace, defense, and so on and so forth. So now, so what have we actually used it for? So just to give you an example of just two customers, right, that have used these physics-based digital twins. The first one is Finis Contact. They create these relays, right, these contacts, right, and if these contacts go down, right, it creates tremendous downtime, right? The entire city of San Francisco, right? If a particular contact relay fails, right, so 10,000 people will be without power. So it's very, very important to predict failures of this contact, right? And so essentially, there is no way to put in a sensor inside this thing, because the contact will stop working like contact if you do invasive things, right? So we have to do this virtual sensoring, right? And that's what we do with the physics-based digital twins. So I'm not going to go to the details, but using sort of this simulation-based digital twin builder, we are able to partner with Phoenix Contact to build very accurate component failures, so they could do the replacement of these contacts before it failed, right? Saving hundreds of thousands of downtime hours. The other example is Volkswagen, right? Where we partner with them on a battery modeling for the electric cars, right? So essentially, you wanted to build a fast electrothermal model to optimize their battery pack, and we partnered with Volkswagen on building electric car that would go on top of Pikes Peak and beat a record, right? It was able to go on top of Pikes Peak in the fastest possible way, beating the world record in any form of car, internal combustion engines, gasoline engines, car engines, whatever, with the electric car, right? And so the point with electric car is that you have an electric motor, you have power electronics to take that electric battery and drive the electric motor and so on, right? All of those things can be modeled through, for example, Maxwell electromagnetic tool, the battery modeling from Fluent, and so on and so forth. So using those simulations, we built a whole system model for the car, right? And clearly you can say, oh, I'm going to make the car very fast by making it twice as big of a motor, right? Well, if you do twice as big of a motor, then you need a larger battery. If you have a larger battery, the size of the battery goes up, the weight of the car goes up, therefore it doesn't go as fast. So you have to do a system level optimization. This is an example of digital twins in the design part. We partner with Volkswagen on building the digital twin of that car, the electrothermal model, so optimized battery pack. And again, when you are doing this, when you're in this competition, you can only do it once. And so it had to be correct the first time around, and we are able to partner with it. So that's an example of how we partnered with Volkswagen. So now let me talk about the really interesting technology, right? How we can combine physics and data analytics to lead a complete solution. This is the most exciting part of my presentation today. So just to recap, as I said, there are two broad approaches to doing digital twins. One is you take a data analytics approach, right? This neural network approach that I kind of talked about, right? You put some sensors on an asset and you build a neural network model, and based on stuff, it is really good, it's most general, but it takes a lot of training data, and it is, if you have not seen that observed behavior of that particular failure mode, it does not work. The simulation-based model, right, which is that bridge example that I talked about, and all the twin builder thing that I talked about, right, is good. It is accurate, but it takes a long, expensive time, right, to do those models and simulations and so on. So it's accurate, but it's expensive. So the question that we had is, can we combine the two? And that's essentially what we are doing, right? So this chart is showing sort of in one slide, right, the ecosystem, right? I mean, how people are using different approaches. So the people who have these large industrial assets, like when I said, right, when I was at ABB, we had all these transformers and switchgear and so on, the Ability platform. So ABB was using a data analytics based digital twin. They own the assets, they collect data on the assets, and they try to predict, hey, this is where things will fail, right? Same thing for Schneider with the EcoStruxure platform, right? So in the automation area, people are using database analytics. In the automotive area, the car companies, BMW, Ford, GM, etc., they are all collecting data on their connected cars and using analytics to drive digital twins, right? Aerospace companies, Boeing, Airbus, or the engine companies like GE, Rolls-Royce, Pratt Whitney, and so on, right? Energy companies, right? Oil and gas companies, Shell, Chevron, or utility companies like National Grid, Duke Energy, they all have large assets. And these people who own the assets, they're trying to build digital twins of those assets and the system of assets, but they're all using it based on data analytics. You have these industrial data platform. These are the people who own the assets and they're doing digital twins. These are people who do not own the assets. They have a software platform like C3.ai, Tom Siebel's company, Uptake, Spark Cognition, and so on, right? They essentially partnered with these companies, right? They take a C3 platform on shell and make it work as a digital oil well, right? Or Uptake with some wind farm companies and use it. Then you have all the cloud service providers, AWS, Microsoft Azure, Google Cloud Platform, IBM, etc., right? Alibaba, Tencent, all of them are doing database analytics. Then you have a bunch of simulation companies like Ansys, Dassault, Siemens, Hexagon, etc., right? They are all doing these simulation-based models. So as I said in the previous slide, right, that data analytics has its advantages, it's general, but it takes a lot of training data. Simulation is very accurate, but it takes a long time, right? So the question is, can we combine? So what we have done this year is to combine AI-based approaches with simulation-based approaches. And this is sort of the workflow that we are actually seeing very successfully deployed in customers. So this is the workflow. I kind of show the workflow as a three-step process: build, validate, deploy. This is what is going on, right? So the build part is you will take an asset. It can be a car, an engine, an oil well, whatever asset that you have, and you model it using the physics, right? This is the symbol for our fluid simulation called Fluent. This is the symbol for our mechanical structure, Ansys mechanical. This is the thing for our Maxwell tool, right? There's electromagnetic. So depending on the physics you are modeling or the multi-physics interactions of fluid structure interaction, fluid structure electromagnetics interaction, you build these things, but the full 3D physics takes a long time. Therefore, you build a ROM, right? And I kind of gave you a one-slide tutorial of linear ROMs, static nonlinear ROMs, and dynamic nonlinear ROMs, right? You take that technology, a set of things, and you build a ROM. This ROM now runs much faster, right? The simulation model would take 1 million hours to run. This ROM runs in a matter of minutes. So that's fast. This model, right, you could take you can actually take a large system like in an oil well, right? You have valves and pumps and so on, and you take all these different components, build ROMs of the components, and build a system model. This system model, in the normal case, forget this thing, right, goes into this deployer, right? This is the twin model for deployment that I talked about, partnering with say, Microsoft's Azure platform or PTC's ThingWorx platform and so on, right? And this is a thing that is running on the cloud or on the edge. This is the normal flow. What we have now done this year is to do this combined Ansys simulation plus data analytics approach with a partnership with a startup called Geminus. So let me tell you the Geminus technology in one slide. This is the only equation slide I will use in my presentation, but it's very, very important. Imagine you have an asset like a wind turbine, right? And the asset, if you look at the physics, that physics is governed through this sort of set of equations, right? Now, you can come up with a really accurate physics-based model of the wind turbine, right? Using all the Fluent and whatever, but that may take you a long time to run, right? So what you do is you do a reduced order model, and the ROM model is not actually measuring the real asset, right? So you can see the ROM, this is the model, this is the blue curve is showing it is slightly off, right? And so you take experimental data at these different points, right? And you say there is an error with this point. So one approach is you can just take this asset and measure these different points. Point number 1, output is Y1. Point number 2, output is Y2. Point number 3, output is Y3. You can take all these different sort of measurements, build a neural network model, and it will model the physics of the wind turbine, but it will take you like 10 billion data points to measure, right? That's the neural network approach. The ROM-based approach is saying, hey, we can take this is a wind turbine, and we'll do this, and this works like this. This is the physics simplified, and that is this sort of slightly erroneous, but it's a model. That's the ROM model. What we're now saying is, hey, suppose we take the ROM model, which is shown in this equation, right? dq/dt is R of Q. That's my ROM model. Then I actually predict the output at time 1, saying Y1 of Q. But I actually measured the output at Y1. So I look at the things, and there's an error. So the error between Y1 and Y1 of Q, the simulated output is this, and there's a difference, and that difference is delta 1. So I look at the delta 1. Then I take the second time step, delta 2, etc. So instead of training this for 1 billion steps, you train it only, you measure the output only 1,000 times. Then for these 1,000 small number of steps, you use machine learning, right? So for a much smaller set of inputs that you are actually measuring, you take this thing and you build that delta field, and the delta field you add as a correction to my friend ROM, right? And this is the ROM plus the delta field is this model augmentation, which allows me to run this thing much faster, right? And so let me see if I can go back to my previous slide or not. Yes. So this is my raw model. I was slightly inaccurate. I measured experimental data with this technology, and output was this is the accuracy, right? This is the combined power of this physics-based simulation and field inversion, right? So again, I don't know if I was able to explain this or not, but this is the core technology. So the combined approach of the physics-based analytics is what we are now providing. Now let's look at what is going on, right? Using this combined approach, what you can do is you can take the physics of whatever asset you have, and you take sensor data, right, of these parts, right? You fuse it together, build a model-based digital system. So now here is the key thing, right? Suppose you are in a digital oil well, right? And you say you have 10,000 pumps and 15,000 valves and so on, right? Now, if you could afford to have sensors on all the valves and all the pumps, you could actually build a very, very accurate model. The trouble is in a real pump, right, a real system, of all the 10,000 pumps, you can only probably have IoT sensors on, say, 10 pumps. Of the 15,000 valves, you can only do sensors on, say, 200 of those, right? So having a subset of sensors complemented by physics, what can you do with model-based digital systems, right, in a large industrial flow network? That is the approach that we are heading towards, right? And so what we have done is we have taken this physics-based digital twin, right, with this high-quality approach, with the hybrid, with the Gemini's technology, right? So the question is, now you have a very accurate model, like what good is the model? The goodness is it allows you to do predictive maintenance, right? So you can proactively detect adverse issues. This is the business value to the customer. Or you can do performance monitoring and say, hey, my oil well is not quite producing 10,000 barrels of oil per month. And why is that? Well, I can monitor it and so on. I can do anomaly detection for an oil well. I have 10,000 wells and one of the wells is not doing well. Go for the anomaly and find it, and then do diagnosis. This is very important, right? Oftentimes what happens in oil well is you are having all, or in a refinery, you're trying to do this refinery and you have to get exactly 92% ethanol, right? For that premium grade gasoline that you buy from Shell. Now, in an oil refinery, you're doing all these things and there are like 20,000 different valves and settings that you do, and you get to 92% ethanol. But suppose the output is 91%. You have to do root cause to say which of these valves is not working well, right? Where is the mixing curve? And it's very, very hard. If you have a digital twin of the whole refinery, you could actually do these what-if scenarios and diagnosis. So lots and lots of applications in a variety of verticals. So the question is, does this work? And this, again, this is a real customer use case. I cannot name the customer, I cannot name anything, but I'll just show you what the beauty is, right? So inside a large customer with a lots and valves and so on and so forth, right? The actual measured data, experimental data, is this red squares, right? And then the model, the reduced order model we are doing was this green chart, right? And so the question is, can I do this combination, right? And get you to that augmented model. And as you can see, the augmented model is taking that green, the wrong thing, right, to the corrected value. Now you will say, hey, all Prith did was do curve fitting, right? I mean, clearly, if I take a bunch of points like this, I can draw a curve that will be right there, right? That's sort of looks like, oh, that's what you're doing. It's not what you are doing. What you're doing is you are doing the training based on, say 100 points, right? And you say, we'll do all this field inversion machine learning to do that model, and that's how you're doing the model augmentation. Then you do it on unseen data. You haven't even seen that data, that failure mode that I was talking about, right? Because you have captured all the physics and a subset of inputs, even on unseen data, the model actually accurates output. This is the beauty of digital twins. So hopefully I was able to explain you what the challenge is and the excitement is of this approach. So that's sort of what is going on. Just to give you an example of the kinds of ecosystems that we are working with, we are working with, so I mean, Ansys is just doing the physics-based part, but we are partnering with different IoT companies, the SAP and PTC and others, Rockwell Automation, they're in an automation setting, right? We are working in a factory setting, right? Building what is called virtual commissioning thing, connecting our simulation-based stuff with their PLCs and drives and so on in a completely digital twin of a manufacturing setting. or we are doing sort of on the cloud, we are partnering with Microsoft Azure. This is why I said Sam George is talking about this same technology in a different conference, at the Azure conference, right? You are partnering with, and again, I talked about the Gymnast technology. So there's a lot of it is partnership with the ecosystem. One of the things that we have recently done is, as this whole digital twin technology is growing, right? There's a digital twin consortium that has been formed with more than 150 members. And if people in the audience are interested, you can go to digitaltwinconsortium.org and find out more information. But what is going on is there are sort of 8 and 5 founding members, Ansys, Dell, GE, Lend-Lease, and Microsoft. And essentially, we are creating a set of digital twin technologies, right? And some sort of test beds and so on and so forth, which is essentially trying to push this technology forward. The other thing that we are working on is a digital twin definition language, right? When you have a large system, like you have a building has an architectural plan, right? And using BIM models and so on. So how do you take a general structure of how you enter a design, right? And typically you have a building, which is a system of systems. A building has 9 floors. In a floor, you have 20 rooms. Inside 20 rooms, you have 53 doors, right? So you can click into different levels and build a complete system level model hierarchically. So we are working with Microsoft on a digital twin definition language, right? Which is, again, will be part of, which will sort of make it available through this digital twin consortium to enable IoT solutions being built out of this system. So I'm just excited about that consortium. And this consortium actually has working groups on taxonomy and terminology, 4 different areas that we are working on in digital twins for infrastructure, digital twins for energy, natural resources, digital twins for manufacturing, and digital twins for aerospace and defense. If you are interested, you should join the consortium. So in summary, I thought I was able to share my personal excitement about the role of digital twins. And it's an accelerating trend in the industry. And as I explained to you, right, so there's this early work which is data analytics based, right, which is easy to use, and you can do it most general form, but it's not quite as accurate, right? And it's that you have to have lots of training data, and it's only limited to the use cases that you can see. Physics based, on the other hand, you can literally do what if scenarios of all kinds of physics, but it takes a long time. The combined approach takes the best of both worlds. It is a general approach, and it gets you the digital twin models of failure modes that you have not seen thus far, right? And essentially what we have been able to show, hopefully through this presentation, is the excitement about the kinds of opportunities that we can solve with these things. And we are now deploying these things at scale, right? For like large oil wells, right? Where we are working with a valve company or a pump company. We are taking these individual components of valves and pumps and deploying in a large network in oil well with 14,000 valves and 20,000 pumps, and saying, okay, in this thing, if you want to get this quality oil grade, we can do it. Or in a semiconductor factory, right? Using semiconductor processing equipment like the PVD machines, CVD machines, and so on, we'll be able, and in those machines, there are like 100 different gases that are combined, right? Once you do this combination of gases, then the right 5 nanometer chip gets fabricated. Well, if you have a defect in that 5 nanometer chip inside a foundry like TSMC or Intel or Samsung, right? Where is the problem, right? Doing that root cause analysis. So we are essentially partnering with the OEM companies in semiconductor manufacturing as well as the end foundries. We are working with the OEMs like the valves and pumps companies as well as the oil and gas and manufacturing. It is a very, very exciting area of work, and I'm happy to answer any questions. Thank you so much.
All right, Prith, thank you very much for the very exciting keynote. Very interesting topic. So I would like to open the floor for questions. Please use the Zoom Q&A window to post your questions in text form. So that's one way that you can ask questions. In addition, you can also use the raise the hand feature in the participants window, and then we can give you the permission to speak and ask your question orally. So either through the Q&A window or through the participants window, whatever you prefer. So I don't see any questions so far or requests. I actually had one question myself, Prith. So obviously many systems today actually are not just a physical system, but a cyber physical system. So they consist not just of a physical component, but also a cyber component. So What does it mean to do a digital twin in such an environment, right? You need to simulate not only the physical components, but also the cyber components, or at least build models for those, I guess, right? So what's your vision? What's Ansys' vision or idea about that space?
That's a great question. Again, because I was trying to keep my talk within a fixed amount of time, I only talked about the physics part. So I should have shown an overview of Ansys. So Ansys is a simulation company. We started with physics-based simulation in structures, then we moved into fluids, then we went into electromagnetics and so on. And now we have the capability of simulating cyber physical also. So we have software simulation capabilities as well, right? With our SCADE suites and so on and so forth, SCADE, Medini and so on, right? So we not only simulate the physics part, the physical asset, but we also simulate the software part and the hardware software combination, which is at the core of what you're talking about. So the same technologies apply, right? In a cyber physical system, again, you have the same thing, right? Think of the combination and you have some inputs, some outputs, right? And you can do it purely based on data analytics, or you can do it based on sort of physics simulation. When I talk about physics, it is basically the combined hardware, software, simulation-based model, right? Which is you take a chip and you're doing simulating at the ones and zeros level and so on and so forth. But the combined approach does work on this system. And actually our customers in the automotive industry and so on, as you know, in a Tesla car, right, 40% of the thing is software. So I'm sorry, 60% is software today. So absolutely great question, but the approach works for cyber physical systems as well. Thank you.
All right, thank you. So we have one question from an anonymous attendee. How does digital twin help in areas like agriculture where physiology is not known?
Absolutely great. And we are actually working in agriculture also. So what I mean, I think what the question is saying that you probably don't know the actual physics of how things happen, right? So there people use sort of, people are actually using IoT platforms in agriculture, and they use sensors and so on. They put sensors inside the soil to see is my moisture right or so on. So essentially, and then people build climate models, right? So when you look at a company like John Deere, they actually acquired a company called Blue River, which is taking the John Deere tractors go over a farm and they actually monitor through those sensors what is the moisture of the thing and so on, right? And how much do I need any pesticide and so on. So they're actually collecting really detailed data at every square centimeter of a farm. That and what with the Blue River technology, they're trying saying, okay, let me see my climate model, how much rain will fall in, say, Napa Valley in San Francisco, in California. And you combine that data, the sensor data from the field with the climate data, and based on it create a digital twin model. And you can actually, what John Deere is heading towards is guaranteeing outcomes to the farmer, saying that if we use our IoT technology, right, we can guarantee the farmer 2,000 bushels of corn. That's the kind of outcomes that are being enabled by digital twins. But I think what your question is saying is, do you have a really accurate model of how that corn grain will grow with these things? And then you need sort of, there are these system level models that you can build, not absolutely at the level of computational chemistry or physics, but there are models that you can actually build. The same thing is happening in healthcare as well.
Okay, thank you. We have another question from Sri Parameswaran. So he's asking, what is the most complex model that can be incorporated? So the question ultimately goes down, how well do these models scale ultimately?
So this is a great question. And so what we were focusing on earlier than this year was on taking the digital twin of a particular asset, right? The asset can be a transformer or robot or whatever. And we were focused on the size of the complexity of the asset. And so some of our models go up to like 300 million mesh points, right? These are really, really complicated models that we are doing, but for a particular asset. Then we started working on sort of system of systems. So we did a digital twin model of a peloton, a set of bikers that are running in a peloton setting, right? To drive, to take like the bike race. I forget that. Anyway, so the question is, if you are at the front of the peloton, right, you are getting a lot of drag. If you're in the back, you can do this. So there are all kinds of stuff they can do with digital twins, with simulation models that say, okay, This is how those people will kind of rotate their positions and so on. So we have started working on system level model. We have now done things with this valve and pump example in oil and gas, where the models are scaling to tens of thousands of valves and pumps in an industrial setting. So these things do scale, but this is sort of what customers are looking for, right? Does it scale and is still accurate? And this combined technology that I talked about is actually scaling and is working, providing the same level of accuracy.
Thank you. Don't see any other questions right now. So actually following up on the IoT example for agriculture. So, I mean, if you want to do that, I say properly, but you almost need to run climate simulations and things like that then, right? To project.
That's exactly what is, so there's a reason why IBM bought this weather company, right? Why did IBM buy the weather company? For this precise thing, right? Because they had the weather sensors, they had the weather simulation capability, and so IBM says, we are going to help this for our customers. That's exactly, anyway, so yes, there is a need for climate modeling simulation combined with collecting data on the climate, right? The sensors and so on. That's how people are building this. It's a phenomenal area. It's really, really exciting. But as I said, so for your audience, right? What people think a digital twin is just a simulation model. A digital twin is not a simulation model. It becomes a digital twin when you take that model and you combine it with two-way information flow from the physical asset and the model, right? So you take that bridge, you take a sensor of the crack and you take it to this thing, and then you have the simulation model of the bridge, and based on it, you predict this is where the bridge crack will be, and you take that model back to the real asset, and you do something with the asset which says, hey, I'm going to replace the asset or repair the asset. That is what makes a digital twin a digital twin.
Okay. We have one more question from Avriel Srivastava. So he's asking, digital twins must run in real time. Does this create a trade-off between fidelity and speed of simulation?
That is exactly the point, right? This is, I mean, great question. Thank you for asking this, right? So when you have and this is precisely why we said we need the ROMs, right? Because you can take an aircraft engine. If you simulate that aircraft engine, those blades and the airflow with turbulence modeling, it will take you 1 million hours, right? So just to model 1 hour of flight, if you take you 1 million hours, it's pretty much useless, right? Because what good is it to predict that this thing will fail after 1 million hours? This is why you need the reduced order model, those approximate models, right? Which is where the linear, nonlinear, etc. Those ROMs run in like literally in real time, right? So at the speed of this thing, right? But as you do this, you lose the ability. This is precisely why I motivated the example with the Gemini flow, right? So that wind turbine example where I showed the ROM, that curve was off from the and then you do that correction, right? And this model augmentation is a continuous correction that is happening, right? So it runs in real time, right? But the early time steps are not as accurate. But with time, with this model augmentation, it just in real time, it is getting more and more and more accurate. This is precisely what is going on, Srivastava, with this solution.
Thank you. So Tulika, our chair, general chair, is actually also asking, is there any real-time deadline for anomaly detection, and what kind of timeline are we talking about here?
So that really depends, Tulika, on the use case, right? I mean, what is the time for you to replace a part, right, in an oil well? So, I mean, if you are on a deep water horizon kind of a thing, right? So you find an anomaly, then you, oh my God, I have to replace a valve. You have to send a thing, right? Send a helicopter back to part and whatever, right? Or people actually do replacement parts on the deep water horizon, right? So that thing will be needed. So depending on the time that is needed for that use case to replace the part is sort of the requirement of the anomaly detection, right? You would try to do as quick as possible because what you don't want is any downtime, right? So in a data center, I mean, the entire audience here is in the IT area, right? People are using digital twins also in data centers, right? In a data center, if servers and so on fail, the power system fails in a data center, bad things will happen, right? For a Google or Amazon or whatever, right? They'll lose millions of dollars every minute it's down, right? So if we can predict the fact that this is going to go down, you can replace the part. What you don't, so let me, Tulika, you didn't ask the question, but let me give you another answer, right? So it is important to get it fast but get it accurately, right? Suppose it's $1 million asset, and you say, hey, I'm predicting it's going to fail, and I replace the part. And in that prediction, my accuracy is 60%. So it's $1 million part, it is 60% accurate, therefore I made a 40% error. I just made a $400,000 mistake to replace a part, which I need not have replaced. This was a challenge as CTO or ABB was facing, right? So we were doing all these data analyst-based digital twins, and we are replacing all these parts, right? Just for that worst case scenario, right? And so with a physics-based digital twin, if instead of the 60%, you can make it up to 95%, then the error is only 5%. Therefore, that mistake, $400,000 mistake, became a $5,000 mistake, or 50,000, whatever the math is, right? So it's much more effective. That's sort of the fundamental reason why the analytics part is doing this, right? But there was, I think, a question that I think one of your audience members, like Trivasava, said, how does it scale, right? So in a large, complex system like a flow network in an oil well, right? You may think that, oh my God, this technology will be super duper good and so on, it will be absolutely accurate. You cannot be absolutely precisely accurate. There's sort of range of uncertainties that we can predict with this anomaly detector and so on, right? So we'll say, okay, so when you are building parts, right, you think it is steel, but the steel quality of Young's modulus of steel has a little variation, right? So that one valve will be slightly different from the next valve, and so all of these valves will be slightly different, right? So there's uncertainties in the valves, and so there'll be a range of variations inside the valves. And so through this digital twin model, we can actually accumulate all those probabilities, and at the end, we can say in the refinery output, there'll be a range of this 92% to 93% with this curve, right? We will be able to do that and say, and when this curve goes there, we'll be able to do root cause analysis of that's the valve we have to change, which will get you to a slide. So it's all the game of probability, right? Essentially, machine learning and all these things are nothing but the fundamentals of Bayes theorems and so on, right? Anyway, I'll end with that note.
Okay, thank you. So I have one question. Where do the digital twins actually run? Do they run at the customer? Do you provide the compute service, or you work with cloud providers? Or can the digital twin actually run in the physical entity itself, right?
They actually run on all of the above. They run on the cloud, that's why we partner with Microsoft Azure. So it's running on the cloud. That's one use case. The other is they may run on an on-prem at a customer, right? So not everybody does things on the cloud. So they will have a high-performance computer at a customer site, or they will run at an edge device, right? So you may have like ARM-based processors, and again, I didn't have time to go into, right, this different sort of systems, is this embedded system, and this is the part of the cyber physical that you're talking about, right? And you can have a small system, so you can and these digital twins that we create are these ones and zeros, and we try to create these things with small memory footprint, and the small memory footprint models will run at the edge, right, or really fast. Now, what we are talking about is some of these things require the use of, again, in neural networks, you know that these things require this weight function that I talked about, right, can be very easily implemented with GPUs, right? So that's why NVIDIA is doing a lot of work on AI, ML, neural networks for this thing, right? So people are talking about putting GPUs inside the edge devices, right? So you do the GPU-based training, the neural network training on the cloud, right, at scale on whatever stuff. Then you build that model and you download this trained model and running it on an edge device. And some of the edge device will be simple things like an ARM chip or whatever, or it can also have NVIDIA GPUs. But that's sort of details. It's a very, very exciting area.
Yeah, it's an exciting space. Yeah. So we're unfortunately at the end now of this. So let's thank the keynote speaker, Prith, again, right? So a virtual hand clapping. Otherwise, I encourage the audience to move on to the technical sessions that are starting now. So we have parallel sessions for CADIS, CODIS, ISSS, and MSOFT going on with